Welcome back to Office Hours with Dr. Clark. Today we are going to be continuing our discussion on SM1 reactions, but specifically we're going to talk about nucleophilic substitution reaction, but SM1 reactions that involve rearrangements. So rearrangements, phenomena that we only see, well, I would say only, but generally at, during these foundational organic chemistry courses, we see them happening with anions. Here, my whiteboard here. Here we go. Rearrangements. The rearrangements will cause constitutional isomers to form that you do not expect. So, for example, that's it. We're going to see rearrangements also when we talk about elimination as well as alkene addition reactions, because all those um, can involve carbocations. So rearrangements occur in order to stabilize the carbocation, right? They don't occur just randomly. So for example, let's say we have this alkyl halide. So it's a secondary carbocation after the leaving group leaves. So what can happen is a hydrogen on an adjacent carbon can shift. So we call it a hydride shift. And therefore the carbocation now is on the tertiary carbon. So it was secondary and now we have tertiary. So rearrangements happen to stabilize. We never go up in energy where we're going to go from a tertiary to a secondary because there's no motivation for that. Rearrangements can also happen with alkyl groups. So for example, here I have another carbocation that's formed. I can have a methyl shift that gives me also a tertiary carbocation. So these shifts occur again to stabilize. So this one right here is a hydride shift. This is a alkyl, specifically methyl shift. Now sometimes we can have shifts happen to give us the same degree carbocation, but the shift happens in order to give me like a resonance stabilized carbocation. All right, so here we have a secondary to secondary shift. But the reason why this shift happens is because this carbon here is now a benzoic carbon, benzoic carbocation, which is significantly more stable than the regular secondary carbocation because of resonance stabilized. Okay. So let's look at a reaction that involves rearrangements. So here, let's take, see, we're going to react this. Let's use ethanol. And then, so we end up with this product, which was maybe not an expected product. Right, so first step, we have leaving group leaving, speaking from a carbocation. Then we have a hydride shift. Then a tertiary. Then my nucleophile attacks. Then, of course, leaving with this hanging out here, not bothering anybody. Then we have formation. So let's look at an energy diagram for this. How the rearrangements look on an energy diagram. First, we have our, let me label these here. So step A, B, C. So step A, we have a carbocation formation. And then we have rearrangements, and then we have a nucleophile attacking. Actually, let me. Okay. Reaction progress is starting for so carbocation forms, rearrangement, nucleophile attack, and deprotonation. This A, B, C, D. So as we're progressively going down in energy, because the highest one obviously is going to be the carbocation formation, then I'm going to rearrange to a tertiary, which is going to be lower than that secondary. Then nucleophile is going to attack, which is going to give me a more stable product because now I don't have a carbocation, but I still have a charged oxygen, which is, not a happy oxygen. So then that gets deprotonated, and then we get a product. So we have 4 homes because we have 4 reaction steps. So rearrangements, it's just another little piece that we see in SN1 reactions that we don't see in SN2. Because SN2 does not have a carbocation, so we don't see that phenomenon.